Alright, welcome. In this video, we're going to talk about tangent plane and normal line. And so, just to remind you of a couple of things that I may have already told you about in this class, or maybe it was last semester in linear algebra, I'm going to talk about the equation of a plane in space and the equation of a line in space before we get going on this. So, just to remind you that if we've got a plane that's going through the point x0, y0, z0, like there, and it's got a normal vector, which is like an orthogonal vector or a perpendicular vector, of n1, n2, n3, which like I showed you that on the diagram, and the equation for that plane is going to be n1 times x minus x0 plus n2 times y minus y0 plus n3 times z minus z0, all equaling 0 together. And I was trying to remember what I thought was important about that, but I think what I want you to remember is that an equation for a plane in space is a linear equation in 3 variables. Now let me remind you about the equation of a line in space. So equation for a line in space that passes through the point x0, y0, z0 and has trajectory, that arrow that you see right there, is going to be L of t is the point plus any multiple of the vector. And this should make a lot of sense, right? Because if I add a positive multiple of that trajectory vector, well, that's just going to get me a little bit farther out along the line that direction. And if I added a negative multiple of v1, v2, and v3, that would take me back in the other direction, and so it would just give me the rest of the line there. And so, that's going to be the equation for the line in space, but, we could probably also combine these things and write it as one vector equation, and that would be x0 plus v1t, y0 plus v2t, and z0 plus v3t. All right, now to give you a kind of just a geometric picture of what we're going to be doing here, today, we're going to be finding the equation of the tangent plane to the surface and the equation of the normal line. The tangent plane is very similar to the tangent line from single variable calculus. Normal line, that's something a little bit different, but we've seen how normal lines or normal vectors were relevant to an object moving, and I forget why, but they're relevant to a z equals f of x and y graph as well. The normal line is going to go through the point of tangency. It's just going to be orthogonal to the tangent plane. All right, now I'm just going to give you the formulas for the tangent plane and the normal line to the graph of z equals f of x and y. So the equation for the tangent plane is going to be z minus z0 is fx times x minus x0. And by fx, I do mean the partial derivative evaluated to the point where x equals x0 and y equals y0. So, like where those yellow highlighted numbers are constants, not functions of x, y, or both. That's not what it's going to be. Okay, and then the equation for the normal line, well, we could just kind of set this thing equal to 0 and get a normal vector, right? Because that was how we found the normal vector, which is like taking the numbers that multiplied by x, y, and z when we set the thing equal to 0. Well, if we set the thing equal to 0, we'd have negative z. So we just need to make sure that our normal vector has negative 1 as a z component. And then we can just use fx and fy as our x and y components of the trajectory vector. So it would be like L of t is equal to x0 plus fx times t, where again, fx is this partial derivative evaluated at the point where x is x0 and y is y0. Y0 plus the partial derivative of f with respect to y times t, and then z0 minus t. That'll be an equation for the normal line, and we'll do a couple of examples here. Okay, so for example, we're going to write an equation for the tangent plane and normal line to the graph of z equals x plus 2 squared minus y plus 5 to the third at the point where x is 1 and y is negative 7. All right, now I'm going to need a z-coordinate to do either of these things, so I'm going to probably start there. I'm going to say, all right, if x is 1 and y is negative 7, then z will equal 1 plus 2 is 3 squared minus a negative 7 plus 5 is negative 2 to the third. So 9 plus 8 is equal to 17. Okay, so I've got my z-coordinate there. All right, now I'm going to need some partial derivatives. So the partial derivative of z with respect to x is going to be 2 times x plus 2 to the first minus 0, because that y plus 5 to the third, it doesn't depend on x. Okay, and then dz dy is going to equal negative 3 times y plus 5 to the 2. Negative 3 times y plus 5 to the 2. I mean, I said it right, I don't remember. But, if I plug in x equals 1 and y equals negative 7, I might get zx of 1 and negative 7 equaling 2 times 3, which is 6. and then zy of 1 and negative 7 is going to equal, when I plug in negative 7, I'll have negative 2 squared is positive 4 times 3 is negative 12. Okay. So the equation of my tangent plane is going to be, okay, fx, or I mean, I guess I could start with z minus z0, z minus 17 equals fx, which was 6 times x minus 1, plus zy, which was negative 12 times y minus negative 7. Right? So that's a good solid example of writing an equation for a tangent plane. And then for the normal line, I might need a little bit more room. But, I guess all we need is the formula for the normal line right there. Okay, so, and you can write this as a, as a vector vertically if you like. That's totally all right. So that would be x0, which is 1, right? Yeah, 1 plus fx was 6 times t. Fy was negative 7 minus 12t. And then z0 was 17, and I'll just put in minus t there. It's always minus t. All right, and that's an equation for the normal line to the graph of this surface at that given point. All right, now here's something we haven't talked about quite yet, where the tangent plane is horizontal. Okay, now I do think that this is not something you need like extra special calculus knowledge or anything to understand. I'm going to draw you a picture of a horizontal plane real quick. All right, so that's a picture of my horizontal plane. Okay, horizontal with respect to the xy plane. And so that's going to be like a z equals some number type plane. So 0x plus 0y plus 1z equals some constant. Okay, well the normal vector to this thing is going to be 0, 0, 1, or a normal vector. And n could be 0, 0, 1. So what I'm saying is that the tangent plane will be horizontal when both of the partial derivatives with respect to x and with respect to y are simultaneously 0. That's what I'm going for here. All right, so what I'm going to need is some partial derivatives. But look, oh no, this is implicit. I'll be honest, I'd kind of forgotten that I had put that there, but I just worked through it, and it's just fine. It's no big deal. We just need an expression for dz dx and an expression for dz dy. So we're going to take it implicitly, and so I'm going to start off, I'm going to take it with respect to x, and so we're just going to proceed as usual. We're just taking the partial derivative implicitly. It's just that z might depend on x, so if I take the derivative of that z squared, that will be 2z times dz dx for the chain rule. So I'm going to do that. I'm going to take the derivative of x squared, that's 2x, take the derivative of y squared, that's going to be 0 with respect to x, and then the derivative of z squared is 2z times dz dx, as I was just saying, and that's going to be equal to 0, which is the derivative of 100 with respect to x. Now if I go and solve for dz dx, I would subtract 2x and then divide by 2z, and I get dz dx as negative x over z. All right, and then I can do the same thing for y, and it's going to look pretty much the exact same. Right? 0 plus 2y plus 2z dz dy equals 0, and I could solve for dz dy, and that would give me negative y over z. And this is great, okay? Because if both of these are going to need to equal 0, then I need both x and y to equal 0, while z is non-zero. Okay, I'm realizing I'm going to need significantly more room than I've got. So I'm going to say, okay, that tells me that I need x equal to 0 and z not equal to 0 in order for dz dx to equal 0. But then this is telling me I need y to equal 0 and z to also not equal 0. Okay, so that's still going to be true. So I need x and y both equal to 0. Okay, so horizontal will be x and y are both equal to 0. Okay, so we're just going to plug in both of those. So that's going to be z squared equals 100, and that could give me z equals 10 or negative 10, but that makes a lot of sense because this is the equation of a sphere. And a sphere would have a horizontal tangent at the very top and at the very bottom of the sphere. And that's going to happen at 0, 0, 10, and 0, 0, negative 10. Okay, so I can just kind of report those values, 0, 0, 10. Coordinates of all points, 0, 0, and negative 10. All points, that's going to include the negative 1 too. So there you go. Okay, the next one I've got for you, this one is related to a multiple choice question I'm going to use on you. So, z equals x squared y plus 1 over 1 plus y squared. The tangent plane, at this point, passes through the point 2, 3 t for what value of t? All right, so this is really just like kind of a normal tangent plane problem with just an extra step added on. So we're going to need, we've got our point, we need our partials. All right, so zx is going to be 2xy. Okay, that's helpful. Zy is going to be x squared plus, okay, so I'm going to think that of that as 1 plus y squared to the negative first. So I'd have negative of that to the negative second power, 1 plus y squared. And then I'd take the derivative of the inside, and that would give me 2y. Okay, and that won't be a big deal because I've got y equaling 0. Okay, that's pretty much it. All right, so at the point 1, 0, 1, so zx, where x is 1 and y is 0, that's going to equal, wait a minute, I feel like I may have messed something up here. All right, yeah, this problem wasn't going to work out the same way as the multiple choice question if I didn't make a little change. So I went ahead and added a 3x to this. So now my partial derivative of z with respect to x is going to be 2xy plus 3. And then it won't change the partial derivative with respect to y. So at the point where x is 1 and y is 0, I'm going to have 0 plus 3 equals 3 is my partial derivative. Okay, and hopefully you're looking at your notes book right now and it's already been fixed. Okay, but for the people in my class right now, it might look a little different, but it'll make the example work way better. So zy at the point where x is 1 and y is 0 is going to be x squared is 1 minus 1 plus 0 to the negative 2 power times 0. Well, that's all going to be 0. So that's going to be 1 minus 0, which is 1. So the plane equation is going to be z minus the z coordinate, so that was z minus 1, equaling the partial derivative with respect to x times x minus the x coordinate, plus the partial derivative with respect to y, so that's 1 times y minus 0, so that'll just be plus a y. Okay, now we're going to plug in 2 and 3 and t. So I'm going to get t minus 1 equals 3 times 2 minus 1 plus y, which was 3. And so all of a sudden, that's a pretty easy equation to solve. 3 plus 3 is 6. That means t is going to equal 7. Okay, so that wasn't so bad, right? Provided that we just kind of followed the steps, and I got the example right so that it wouldn't, be impossible. I don't think that was going to be possible if both of the partials were 0 and 1. Yeah, I think x was going to be fixed at 1, and so I wouldn't be able to go to 2, 3, and t because x was only equal to 1. But that's, t equals 7 is going to be the answer to this example the way I've changed it now. All right, now here we've got basically a table problem. It's not written as a table, but it's just giving you data. Write an equation for the tangent plane to the surface defined by the equation f of x. Oh, yes, I remember this. Okay, this is also getting yeah, so this is a function that takes in 3 variables and gives you back and forth. Okay, so the surface defined by the equation f of x, y, and z equals 5 at the point 2, 3, and 4. This is a situation where I'm going to have to give you a more general equation for the tangent plane. All right, there you go. So if we've got an implicitly defined surface, this is going to be an equation for the tangent plane, and that's what we're going to need for this one. Now, it's an implicitly defined surface because it's it's a level surface of this 4D function, where we're taking in 3 dimensions and giving back a fourth. But, it's not impossible to visualize. You can think about the temperature of a point in space. Right? Point in space has 3 coordinates, and the temperature is a 4th coordinate, so it's not that hard to envision the possibility of it. But from here, we're just going to be filling in the pieces. So fx was 6, so 6 times x minus 2, plus fy was 7 times y minus 3, plus fz was 8 times z minus 4. That's going to equal 0. Okay, and that's the equation for my tangent plane to the surface defined by the equation f x, y, and z equals 5. Okay, so that was a little different, but that was one, it'll be relevant for your multiple choice test. All right, and now the last one I've got for you is find a normal vector to the surface xyz equals 9 at the point 1, -3, -3. I think I need another more generalized formula for you here. Right, so kind of like the other one, it's very similar. And we will need to take the derivative of, yeah, this xyz with respect to x and y and z. Okay? And it won't be a big deal. Let me actually think about this. Yeah, in retrospect, I kind of regret showing you what I showed you there, because I think we're just going to take the derivatives implicitly and use the same formula we've been using over and over for this normal line. I think that's going to be the way to go. So I'm going to say, all right, we're going to take the derivative implicitly with respect to x is going to give me yz, or no, pardon me, it's a product because z depends on x. So it's going to be take the derivative of x, leave yz the same, and then I'm going to leave x the same, while taking the derivative of yz, which would be y times dz dx. Okay, and that's going to be the partial derivative of that side equaling the partial derivative of 9 with respect to x. That's going to be 0. Okay, and then I can just plug in x, y, and z to figure out what the partial is. Y times z is 9, plus xy is -3 times the thing I'm eventually hoping to find. That's equal to 0. So that means that dz dx is 3. Okay, and then on a y level, and that might have been a linkage error as well, we don't have to worry too hard about that. We're not taking a standardized AP exam for this class. Taking derivative with respect to y, take the derivative of y first and leave x and z the same, then leave y the same and take the derivative of xz with respect to y. So xy partial z with respect to y. And then I'm going to plug in these points. Xz is -3 plus 9 dz dy, that is going to need to equal 0. Okay, and so dz dy is going to be 1/3. Okay, now I've got the ingredients I need. L of t is going to be equal to x0 is 1 plus 3t. Y0 is -3 plus 1/3 of t. And then the z-coordinate minus t. Now, I do recognize that I may be missing something here on this particular example. I've kind of scratched through and worked this a couple other ways. I really do think there's something I'm missing on this, and I think I'm just going to leave this video here and maybe post follow-up in the future, or maybe if somebody sees what I'm missing, they'll be able to tell me about it in class or down below in the comments. But that's going to be all for this one. Thanks for watching.